Um, we're going to start now. My name is Jonathan Weiss, and to my right is Chris Rollins. So we're in a seminar room here at the University of Potsdam. And so we'll be talking to you on the World Wide Web, but there is a group of people in the classroom. So if we tend to look away from the camera, that's why.
We're doing awkward family photos and looking off to slightly off now, but yeah.
So let's begin. Thanks everyone for joining. So again, my name is Jonathan. I'm at the University of Potsdam now. I was formerly in Leeds with the COMET group, and Chris is now in Leeds as well. I think it's just coincidental that we're both gringos or Americans, but so COMET is the Center for Observation and Modeling of Earthquakes, Volcanoes, and Tectonics. It's a group that uses satellite-based and ground-based observations to study active deformation processes associated with volcanoes and faults. So the bulk of this work that we're going to be talking about is done sort of with COMET. Now I'm in Potsdam with a group called Strategy, which stands for Surface Processes, Tectonics, and Georesources. They tend to focus efforts on the northwestern Argentinian Andes, but they're also supporting sort of the continuation of this work that we're going to talk about today. So we're presenting on some of our work on mapping strain and velocity and earthquake hazard models. My portion of the talk is going to focus on that, and I'm going to sort of introduce some of the work that COMET has been doing over the past few years, particularly related to high-resolution mapping with InSAR, or interferometric synthetic aperture radar. And then I'm going to hand the mic over to Chris, who's sort of taking the work to the next level, where he's integrating these geodetically derived velocity maps and strain maps to try to improve earthquake hazard models for the region. So we're focusing on Anatolia. There's a record of historical seismicity. The deformation rates are relatively high. There's been a long history of work done there, but then ultimately the goal will be to expand beyond Anatolia, and we're already starting to do that. So this work is not done in a vacuum, and just briefly want to acknowledge many people who've been involved in this work over the years. There's Tim Wright, who's the director of COMET, based out of Leeds. Richard Walters is in Durham. Yu Morishita is on loan from GSI in Japan. He's been instrumental in some of the time series work I'll be talking about. Milan Lazecki, Hua Wang in China, Ekbal, who's now at the BGS, Andy Hooper, of course, Karsten Spans, Pablo Gonzalez, Chen Yu, Zhenhong Li, Barry Parsons, Emma Hatton, and Nick Green. All these people have been involved in developing the tools that I'm going to be talking about for the next 20 to 30 minutes or so. So why do we care about this? On the left is a map of strain rates. So this is on the western coast of the United States. The San Andreas Fault here is highlighted with this region of very high strains. You can see on the right is the seismicity. So there's a really strong correlation between strain rate, and in this case, it's measured using satellite geodesy. And on the right, the earthquake rate. So just these data in this model is from the global strain rate model. So the GSRM, which is derived from a large compilation of GPS velocities. And just to remind you, so again, we're showing strain rate, but if you have very good characterization of the velocity field, you can take the derivative of that velocity field, and then you get the strain rate. So in this case, you have a rapid velocity gradient as you cross the San Andreas Fault, and that corresponds with very high strain rates, which then again tend to correlate with where you have earthquakes. So another point worth mentioning is that 96% of all earthquake deaths occur in regions with fairly rapid strain rates. So 1 millimeter per year over about 100 kilometers, that's equivalent to a strain rate of about 10 to the minus 8 per year. So if we can measure strain using techniques such as satellite geodesy, we can improve these estimates of seismic hazard. But again, we need to have accurate measurements of the surface velocities and the corresponding strain rates. So why do we even want to bother with InSAR? The strain rate map I just showed you is using GPS data. GPS data are great. So here's the GSRM, again, the global strain rate model version 2 compilation of surface velocities for the Alpine Himalayan belt. And what you can see is that in some places we have fairly high density of GPS measurements, whereas in other places, on the Tibetan Plateau, for example, we have holes in this coverage. In Anatolia, we have very good coverage. Also here in Greece, the Dead Sea Transform is well covered. But in some other regions where we have deadly earthquakes, we have hardly any GPS or GNSS data. So I'm going to use those two terms, acronyms interchangeably, GNSS and GPS. And so essentially what you see again is that we see gaps in GPS coverage that tend to be also in more slowly deforming regions. In places where we know there are active faults, we've installed GPS networks and we can measure those rates. But it tends to be in these other regions where we want to do better. So what's the result of these holes in the GPS coverage on the corresponding strain rates? Well, I'm going to show an example of the Alpine Himalayan belt. Again, this is strain rates from the global strain rate model. And what you can see is that regions of high strain tend to correspond with places where we have lots of measurements. Those are these black triangles where we have GPS sites. In between these regions, you see large gaps. Sometimes the coverage or the distance between sites can be on the order of tens to hundreds of kilometers. And then you see a lot of interpolation related artifacts as you try to go from velocities to strains in areas where you don't have observations. So this is why we want to use InSAR. So on the left are some synthetic velocity fields associated with a locked strike slip fault. The upper left corner is the surface velocities, and then the lower left is the corresponding strain rate. Now, if we try to recover these model observations from what would be a typical GPS network, shown here in white triangles, what you can see is that we don't do very good, particularly recovering the velocity field. So you see we're only capturing some portions of the velocity field. And then furthermore, for the strain rates, again, we don't quite capture that fault at all. Now, if we add InSAR into the mix, so here's some synthetic InSAR data denoted by these white rectangles, we do a much better job now of characterizing the velocity field at high resolution and with good detail. And we also do much better of recovering the strain rates. Still not perfect, but we can see that we localize it to similar to what it looks like in the synthetic case. So the Sentinel I, which is the European Space Agency constellation of SAR satellites, is a game changer for tectonic InSAR. So previously we couldn't necessarily measure surface displacements everywhere using SAR data. But now with Sentinel I, which was launched in 2014, we can do a far better job. So Sentinel I acquires at least two images every 12 days for the global tectonic belts. These data are free and open, which is a unique characteristic of the Sentinel I data. And then COMET, the group in the UK, is mass producing interferograms with the primary aim of measuring tectonic strains. So here's a map showing coverage, Sentinel I coverage. So there's two satellites, Sentinel 1A and Sentinel 1B. And in Western Europe, where we have this red crosshatch pattern, we get an acquisition about every 6 days. That's a SAR acquisition, also for Hawaii and other, primarily Western Europe. And then in places where you have the green crosshatch, you get an acquisition about every 12 days. So this is the COMET Licks Sentinel I InSAR portal. It's this data portal that COMET's been developing over the past few years. And so what we've done is broken the world up into these frames. So these are frames of both ascending and descending data. And essentially, if you go to this website and you click on one of these frames, it brings up a list of interferograms that you can download for your area of interest. So I'm just showing here the Alpine Himalayan belt, but it's being done globally. The Alpine Himalayan belt is where we're focusing our efforts. So you can see that the frames are color-coded by the number of products, or essentially the number of interferograms. And what you'll also notice is that we've processed a tremendous amount of data in Anatolia, and we're working on filling in the gaps across other portions of the world. So what you can do is you can go and download things like co-seismic interferograms. So this is an example of the January 24th magnitude 6.7 earthquake that occurred in Turkey along the eastern Anatolian fault. And you can see this sort of characteristic fringe pattern associated with a strike slip event. So if you go to the Licksar portal and you're interested in working on a particular area, and you don't see that there's much coverage for that frame, we now have this thing called the Lickspass frame request. So you can put in the frame of interest for your particular study area, and then that frame will be prioritized so that you can get your stack of interferograms. So in addition to co-seismic studies, what we're actually interested in doing is time series and velocity analysis. So this flow chart just demonstrates briefly the processing workflow for the LIX portal. So basically you take your SAR images, you put them through an InSAR processor, and then out comes a stack of interferograms. Precise orbits are used to create these interferograms. There's also unwrapping, so you can download both wrapped and unwrapped data. Ultimately, we will also incorporate atmospheric corrections into the mix, but currently this has to be done independently. So this is a network, a temporal and perpendicular baseline network that would be characteristic of a stack of Sentinel I interferograms. Each black dot represents an acquisition, and each line connecting the dots represents an interferogram. So you can see in this particular network, there's about 429 interferograms that were used. This stops in late 2018, so currently we have quite a bit more data. What you'll also notice is that the number of acquisitions, which is indicated by these black dots, increases when Sentinel 1B went online. So prior to mid-2016, we only had acquisitions for this part of the world where this plot represents about every 12 days, and then afterwards it went to every 6 days. So compared to NBSat, which is an older generation of SAR satellites, you can see that there's been quite a drastic improvement in the amount of data that we're now collecting. And this can help with a variety of things like knocking down your errors, also creating long time series. So in this example, which is also from Anatolia, from the work of Hussein et al. 2018, there was only 75 interferograms used to create this network. And now, I'll show a velocity map for this bottom network where we're using 429 as of mid-2018 and probably around 600 for the updated network. So in order to do time series, to measure time series and velocities and ultimately strain rates at high resolution, you need to take a stack of interferograms. And essentially, in theory, it looks like this. You have your interferograms, you put these through a time series processor, and out comes an average velocity and time series for each pixel. In practice, it looks something a little bit more complicated. Fortunately, Morishita-san developed something called Lickspass recently, which is the Lixar time series and velocity analysis routine. And you can see more details about Lickspass in a recent publication in remote sensing. Now, Lickspass is free to download and quite easy to install. It's Python-based, and it's meant to integrate with Lixar. So essentially, you download the Lixar products, you install Lickspass, and then you can do time series analysis on your own on your desktop. So I'm just going to briefly highlight some aspects. So where the Lixar products are geocoded to about a resolution of about 100 meters per pixel. The default downsampling that's done in Lickspass takes that resolution to about 1 kilometer per pixel. So there's some multi-looking involved. Then there's some quality control checks, identifying bad data using things such as loop closure. Then there's the velocity inversion itself. And then finally, you get cumulative displacements and velocities, and then there's some masking that's done at the end. So I'm going to talk in detail about a couple of these steps briefly. So first, for the GACOS atmospheric correction. So GACOS is the generic atmospheric correction online service. It's been produced by COMET researchers based out of Newcastle University. On the left, you see an uncorrected interferogram. So the standard deviation of the phase is about 6.4 radians. Here is the delay map produced by GACOS. And then when you apply it to the interferogram, you essentially remove this ramp and some of the topographic effects, and you essentially reduce the standard deviation of that particular interferogram by quite a bit. So here are examples from the frames from Anatolia that I'll be talking about. Essentially what you want to pay attention to is that these scatter plots tend to fall to the lower right-hand side of the 1-to-1 line, and that means that there's been a reduction in the standard deviation after applying the GACOS correction. So in general, we see about a 20 to 30% reduction in phase and velocity associated with these GACOS corrections. Now, ultimately, GACOS will be directly integrated into Lixar, so you'll be able to download corrected interferograms and the corrections themselves. Currently, you have to do that correction by going to the GACOS website independently. So next is the inversion. I'm not going to talk in too much detail about this, only that When you have a full rank matrix to invert, you can do this simple inversion, but oftentimes in these networks, you get gaps. And to deal with that, what Morishita-san has invoked is a NS-BAS style approach where there's some temporal constraint on the velocity inversion. So here's an example where you have a gap in your network of interferograms, and we can use the NS-BAS approach by assuming that the velocity is linear in time to sort of get a more realistic estimate of the cumulative displacements across where this gap might be. So finally, we do some masking, so you get this nice velocity field, but there is some noise that's still left in that velocity field. So what's done in Lickspass is a masking based on a variety of parameters. So these 6 bottommost panels are these different masking parameters. I'm just going to highlight. So for example, this is a mask based on the number of gaps that are in this SB or short baseline network. So in this case, we're applying a mask of 10. So any pixels that have more than or any pixels associated with more than 10 gaps will get masked out of this velocity field. Another one is based on the standard deviation of the velocities. So there's a bootstrapping involved in the velocity estimation. And so there are some errors associated with that bootstrapping, and we can also mask based on that criteria. So all of these masking criteria can be fine-tuned by the user. Ultimately, you get a velocity field that looks like this. This is the unmasked velocity, so you can see there's a nice sharp transition, perhaps associated with a strike-slip fault. And then the masked velocity looks like this, so we've reduced these areas with a lot of noise. So again, that frame happens to be for a portion of central Anatolia, crossing the northern Anatolian fault. So now I'm going to get into the more Anatolia-specific portion of the talk. So again, this is one of the Licksar frames that we've processed for Anatolia. You're looking at line-of-sight velocities. So everything in blue is moving towards the satellite. So the look angle, the line of sight is to the right. So everything to the blue, in blue is moving towards the satellite. Everything in red is moving away from the satellite, excuse me. This is the network associated with that one particular frame. So if you weren't so sure what I was referring to when I mentioned gaps, this is what I'm talking about. So you can see here, the network is shown in blue and red. Red connections are interferograms that were discarded during the quality checks, which result in gaps. You can see here that they tend to correlate, in this particular case, with winter months, probably because there's snow cover, resulting in decorrelation, and our inability to bridge these gaps when we do our inversion. So in this case, we have 2 gaps, but we can get across that because we're using this NS-BAS style inversion. The other thing to note is that because we're processing in these Licksar frames, the reference point for each velocity map is independent for each frame. So the next thing that we do is we transform these velocities into a Eurasia fixed reference frame using GNSS or GPS data. In this case, it's a compilation from Jean-Mathieu Noquet and Philip England. These culled velocities tend to have significantly lower errors than some of the other data sets that are available out there. So this is the velocity field that we're using to tie the Licksar frames to a Eurasia fixed reference frame. Here's the map now of ascending data for all of Anatolia. And so these are the descending data. So what you can see is now that we have nearly complete coverage, and you can see also that there's this nice sharp transition in velocity associated with the northern Anatolian fault. Just some statistics associated with this data set in particular. So we're looking at about 5 years of Sentinel I data. There's about 200 images per frame, resulting in about 8,000 images for the entire data set. And then there's about 800 interferograms per frame, resulting in about 30,000 interferograms for this Anatolia product. And this covers an area of about 800,000 square kilometers, which to our knowledge is the largest estimate of interseismic velocities from InSAR to date. We also, with InSAR, you're typically interested in the uncertainty associated with these measurements. So what we've done is one way to estimate uncertainties is to look at the overlaps between frames, both along and across track. And we create standard histograms of those differences. And then we can get an estimate of the line of sight accuracy. So in this case, we're seeing an accuracy of about 2.5 millimeters per year on these measurements. We can also make another measurement of the accuracy of these line of sight velocities. So now I'm showing Remember I mentioned that there's some bootstrapping involved in the velocity estimation in Lickspass. So here you can see how the velocities decrease as you lengthen the time series associated with the velocity. So initially, when we only have a few interferograms going into the network, we have fairly high uncertainty, and then these tend to drop off quite quickly with time. We can also estimate the uncertainty by calculating semi-variograms. In this case, it's for one of the frames that's not near any of the faults. We've also removed the tectonic signal, and we've done some masking in places that are moving up and down quite rapidly, and I'll talk about where we get those estimates from in a second. Again, you can see these semi-variogram-based estimates, which are at different length scales, so 50, 100, and 150 kilometers, also decrease quite rapidly, although they don't converge with the bootstrap-based estimates for a variety of reasons, probably because we're not doing a perfect job of tying these data to the GNSS, or that there's some uncertainty in our tie to this Eurasia fixed reference frame that's based on the GPS data. We can also compare these to theoretical estimates derived from an analysis of continuous GPS data. And again, we see, so the different lines represent different acquisition frequencies for your observations. And again, you can see this sort of same quick reduction in errors that are sort of converging with the bootstrap-based estimates, but there is a little bit of a difference between the theory, the bootstrapped estimates, and our semi-variogram-based estimates. So from the semi-variograms, we get an error of about 2.5 millimeters per year. That's at this lag distance or length scale of interest for tectonic studies of about 100 kilometers. So we're seeing agreement between the overlap-based histograms and then these semi-variogram-based estimates. So I've sort of been alluding to time series. Now I'm showing velocity maps here, but the other nice thing about Lickspass is you get these time series of displacements for your network. Here's an example from a place called the Konya Basin. So you might notice that there's this difference in the direction of the velocity in this region. And here's the associated time series. So this is of one of these red points with respect to a point that's outside of this region of red. And essentially what's happening is here is you have groundwater exploitation and rapid subsidence of the surface at a rate of about 50 millimeters per year. So this is another nice thing that comes out of Lickspass. You get the velocity fields, and you also can look at some time series. And in this case, we're fitting some seasonal trends to these data. But one thing worth mentioning is there is this ambiguity associated with interpreting the line of sight information. So line of sight is composed of deformation that's coming only in the look direction from the satellite. So this can be composed of horizontal motion and vertical motion. So in order to look at that, what we do is we can decompose the line of sight velocities into north, east, and up components. And we do that by inverting this equation where we have velocity line of sight. In this case, we have two directions, ascending and descending. We have the incidence angles associated with the satellite paths. We also have the satellite headings. And then we want to get our 3D velocities. However, InSAR is notoriously insensitive to motion in the north direction. So it senses well east, west, and vertical, but it doesn't do particularly well with north. So in order to constrain the northern component, we actually use that same GNSS velocity field, an interpolated smooth version of it. And then what we can do, so there's the example, that's the smooth northern component of the velocity field from GNSS. And then here's the example of the east-west velocities that come out of that inversion. So what you can see is this very sharp transition across the northern Anatolian fault, where everything south of the fault is moving to the west. Everything north of the fault is essentially stable. You can also see a velocity contrast associated with the eastern Anatolian fault. And this is kind of at unprecedented resolution considering the scale. There's also some known creeping segments associated with Izmit and Izmit Pasha right here that you can also see very sharp changes in the velocity associated with this. So again, this is at about 1 kilometer resolution. In comparison to some of the previous work that's been done in Anatolia, so the top now is showing about 8 years of NVSAT from the work of Iqbal Hussain in his 2018 paper. So the polygons show where you have information in both ascending and descending directions. There's a gap in between. You can see there's some noisy patches. The middle plot is the velocity field after about 1.5 years of Sentinel I data. So this was done in about mid to late 2015, early 2016. And now after 5 years, we paint this really nice picture of this Anatolian surface velocities. In comparison, so Tim Wright, who's, as I mentioned, the COMET director, the majority of his PhD was done processing just 2 NVSAT tracks. And that was this sort of early result where you can see a nice contrast in velocity. So whole PhD just to create this small postage stamp of surface velocities. And now we can do this fairly automated using Sentinel I data and some of these tools like Lix and Lixar and Lickspass. So again, I said we're solving not for the east-west velocity and the vertical velocity. So here's the vertical velocity map. You can see that we, again, this region that's subsiding rapidly associated with groundwater extraction. Some other spots, there is some noise in here, but essentially now we also have a nice picture of vertical motions that would be attributed to anthropogenic processes. So the next thing we want to talk about is how we go from velocities, or how we go from line of sight velocities to not do this decomposition where we use the GNSS to constrain the north-south, but actually directly inverting the line of sight data for velocities and strain rates. And we do this with the BellMap software that was developed by Hua Wang and Tim Wright. It's based on some equations from England and Molnar 97 and 2005. And essentially, we break our area of interest into a triangular mesh, and we solve for the velocities at the corners of the triangles using our observations from within the triangular mesh. And the modification, so the adaptation from England and Molnar was that now not only are we doing this for GPS velocities, but we're directly inverting the line of sight information. So we're not decomposing it, we're directly inverting both GNSS and line of sights. And there is some regularization required that impacts sort of the strain rate magnitudes that we end up getting out of this approach. But so here's the example of the mesh that we're using for Anatolia. In this case, we know where the fault is, and we use it to constrain the mesh triangles. So we don't want meshes that cross this fault to try to reduce the amount of smoothing. We also have a finer mesh around the fault and a coarser mesh outside of the fault. But again, in regions where we don't know where the faults are, we can just use a constant size mesh. So first, here's the strain rates, but just using the GPS data. So now we're inverting only for using the GNSS for the surface strain rates. The GNSS are indicated by these white triangles. And now I'm just going to show you the difference between what happens when you incorporate the line of sight measurements as well. So again, this is the inversion of the GPS plus InSAR. This is GPS only. And you can see how much better we do in terms of localizing high strain regions along the northern Anatolian fault. We also get some high strain along the eastern Anatolian fault. That's not so apparent in the GPS only version. There's some off fault high strain regions actually in both versions, perhaps associated with this western Anatolian extensional province. Not so much here with the central Anatolian fault zone. So now I'm showing another component of the strain rate tensor. This is the dilatation field, which is contributing to some of these patches that we see in the second invariant strain rate. And so the dilatation rate field is associated typically with expansion and contraction, perhaps with normal faulting, extension or thrusting, and also with anthropogenic processes. So we can also look now at the maximum shear strain rate that is an indicator of where you have strike slip motion on some of the major faults. And you can see that it cleans up tremendously. So essentially we're kind of disregarding places that perhaps are extending or contracting. We're throwing out some perhaps of the man-made anthropogenic signals. And now we get very nice localization, a very clean picture of high strain, including along the eastern Anatolian fault. I'm going to quickly overlay shallow crustal seismicity, and in particular, draw your attention to the 2020 magnitude 6.7 event that occurred here in a region where you have moderate strain. Now, northern Anatolian fault is straining at much faster rates, but you do see that we get some localization of strain on the eastern Anatolian fault. So if you want to read more about this work, check out our paper on the Earth Archive preprint service. It's in review now at GRL. And now I'm going to hand the floor over to Chris, who's going to talk more about how you can actually turn strain rates, geodetically derived strain rates, and seismicity into probabilistic estimates of earthquake hazard. So essentially the next step.
Okay, so now that we have this strain rate map, let's look at what we can do to use it to help place constraints on the seismic hazard in Anatolia over the long term. So we know from examples around the world that strain rate is a pretty good proxy for earthquake potential, earthquake rate, earthquake activity, and earthquake hazard. This is shown here on the left for the case of the San Andreas fault system in California, and then on the upper right for the junction of the North and East Anatolian faults. But are there particular measures of earthquake potential that we can directly estimate quantitatively using strain rate? Well, this is the full version of that figure on the upper right with the North and East Anatolian faults, and it actually shows us two such measures. So on the left, we have the strain rates estimated from previous geodetic data. On the right, we have the earthquake rate in each spatial bin above a given magnitude. And in the middle, we have the total seismic moment rate, or seismic moment release rate by earthquakes in each spatial bin. Basically the summed earthquake size per unit time in each bin here. And you can see that the three are correlated. And in the remainder of this talk, we'll look at a way to use the strain rates to estimate what both of these parameters might look like in Anatolia on a regional scale over the long term, and how they may be tied to one another. So what we're going to do is we're going to use the strain rates to estimate how quickly seismic moment is building up in the crust of Anatolia, and then compare that to the rate at which earthquakes are releasing seismic moment in and amongst themselves. And what we're going to do is we're going to make the assumption that on the long-term average, those two rates should balance one another or be equal. That is to say that earthquakes will release the slack in the system in terms of moment at exactly the rate at which the slack accrues via the geodetic processes we image here, such that no deficit or surplus in seismic moment accrues over the long term. And that sort of makes intuitive sense. It's just it's usually moment balance or moment conservation. And so our first challenge is how to convert strain rate to moment buildup rate, how to use strain rate to estimate the moment buildup rate in the crust. For that, we'll use the formulation of Kostrov, 1974, which tells us that the moment buildup rate in a given volume is the strain rate in that volume times the shear modulus mu, or the elastic stiffness of the volume. So we're going to do this in each little cell of our strain map that we have here, and then take the sum at the end in a few slides later. But in each little cell here, so we know the strain rate of the cell from the work that Jonathan has done. We know the surface area of each cell, the area covered by it. What we don't know as well is the vertical dimension of the volume, which is the locked depth down to which the straining applies or holds physically. But we can turn back to Iqbal Hussein's work. He looked at a lot of previous InSAR data around the North Anatolian fault and found that the locking depth on the North Anatolian fault is pretty solidly in the range of 16 kilometers plus or minus over most of the length of the fault, as you can see fit to these arctan functions here of the geodetic data. And because the North Anatolian fault is the major player in strain accumulation in Anatolia, we're going to make the assumption that that 16-kilometer locking depth is a pretty good representation of how deep the strain accumulation might apply throughout most of Anatolia. Most of the strain accumulation is on the North Anatolian fault anyway, so that should get pretty close. So just to be clear, this is assuming that we are continuing what we infer at the surface as far as the strain rates down to 16 kilometers uniformly, making basically a 3D model. And then the last parameter we don't know is the shear modulus. Here we're going to assume a uniform shear modulus of 32 gigapascals, which is the volume for granite. Now the shear modulus for sure will increase with depth in the crust, but it may also decrease around faults due to fault damage and other factors. So we don't know which side of 32 gigs it's going to fall on. So we're going to use that as our value for our purposes. So using that, we can convert our 3D strain rate model to a 3D moment deficit buildup rate model. And then this is the map view of it, and this is the moment deficit buildup rate per cell, now summed down depth. And so it just is a scalar function of the strain rate, as it should be from the way we've plugged it in. And if you sum up all of these cells and the moment buildup rate in them, you will get the value at the peak of this PDF here down on the bottom right, which is the total rate at which seismic moment is accruing in this region around Anatolia per year or per unit time. And that's the quantity we're going to be using compared to earthquakes going forward. And that total rate is 2.5 times 10 to the 19th Newton meters per year. Now, what does that mean? Well, the moment release in an earthquake is given to us by the good old moment magnitude equation. And so for reference, 2.4 times 10 to the 19th Newton meters per year is equivalent to the moment released in an 8.0 earthquake if that earthquake happened every 50 years. Another way to say that is, if an 8.0 earthquake happens somewhere in Anatolia every 50 years, that alone would release all the slack in the system. The same job could be done via an 8.5 earthquake every 300 years. The moment deficit buildup rate is also equivalent to 2 magnitude 8.3 earthquakes every 300 years. And you can kind of see the issue with me expressing it this way is that I can make this sound as innocuous or as scary as I want by a completely arbitrary magnitude that I throw up here. The other problem with this is that no matter what magnitude I would put up there, it would belie the fact that over any appreciable amount of time, earthquakes come in a variety of sizes from large to small, and it is going to be the continuum of those sizes that sort of teams up to release the slack in the system at the same rate that it's accruing over the long-term average. So now we want to look at how small and large and moderate earthquakes might specifically pair up to do so. What would be the partitioning? Would small earthquakes do most of the work, or would large earthquakes do most of the work? And what are the numbers? So for clues on that, we can turn to the instrumental earthquake catalog in Anatolia. And that is plotted here. This is compiled by Kadir 2018 as part of a recent effort to update the Turkey National Seismic Hazard Maps. And so this catalog has been normalized as far as magnitudes and combines a lot of different data sets and a careful eye for good and bad data and constraints. And so you can see the 1939 Erzincan earthquake, a magnitude 7.8 earthquake over here on the eastern stretch of the North Anatolian Fault. This is that junction that we saw in the first couple slides of this section with the East Anatolian Fault. You also see the Izmit earthquake, the devastating earthquake of August 17th, 1999, up here on the top left, just east of Istanbul. And you can also see the 20th century sequence of magnitude 7+ earthquakes, including the Düzce earthquake, which happened a few months after the Izmit earthquake. You can also see small and moderate and some large earthquakes scattered throughout the remainder of Anatolia, and these are colored by their year of appearance. And we can plot that against the moment deficit buildup rate, and like Jonathan's comparison of the strain rates, they spatially are fairly well correlated. And we are not going to use this spatial correlation per se in this next part. All we're going to use is the total moment buildup rate and compare that to the release rate of earthquakes of different sizes. So what we're going to do is we are going to make long-term earthquake models for Anatolia that implicitly balance this moment budget, as it were. That is to say, the earthquakes in these long-term earthquake models will happen at the right set of rates as per their sizes, that they will team up to release the slack in the system as fast as it accrues from the geodesy. And once we hand ourselves each model that does so, we're going to ask the following question. If I were to sit and watch this model go for 112 years, which is the length of this refined seismic catalog, would the seismicity from it look anything like what we've observed in the instrumental record? Now, it's probably not fair to impose that the seismicity, the earthquakes would need to happen at exactly the same places or at exactly the same times. But one standard that it might be fair to hold such a long-term model to is that the total distribution of earthquake sizes should not look completely incomprehensibly different from what we've observed in nature over the past century. That is to say, if that long-term earthquake model spat out 5 9.0 earthquakes in 112 years, that's probably not a very good model for Turkey, because we have no record, fortunately, of 9.0 earthquakes in Turkey. There's no evidence for that. And likewise, and probably more relevantly, if this long-term earthquake model only spat out earthquakes up to magnitude 5.3, and they never got above that. That's not a good model for Turkey either, because we know about these 7.0s and the devastation they've wrought. And so we want something in between these that we can test based on its fit or misfit to the distribution of earthquake sizes in the instrumental catalog. And that is formally called the magnitude frequency distribution. And we're going to be switching to magnitude frequency space for the remainder of this talk in a moment, based on that. And we're going to more directly ask the question, this long-term model A that I handed myself, what are the odds that if you watch that model A go, it would serendipitously give you the exact right magnitude frequency distribution of the instrumental seismic catalog within a 112-year period? So we'll talk about that more in a sec. So this is the magnitude frequency distribution, or the distribution of earthquake sizes in the instrumental catalog, this tan line. So the axes here, we have moment magnitude on the x-axis, and then for each value of moment magnitude, the position of the brown line in Y is the rate of earthquakes greater than or equal to that magnitude. So what we see is once a year, somewhere in Turkey, in the last 112 years, we've had about one 5.7 or greater earthquake somewhere in Anatolia. And once every 10 years, over the past 112 years, we've had about one 6.9 earthquake somewhere in Anatolia or greater. And then we go up to a single magnitude 7.8 earthquake in 112 years, giving a rate of 1 over 112. That's why it sits just below the 1 over 100 line as far as rates go. And then when we get to 7.6, we throw in the Izmit earthquake as well as the Erzincan earthquake. We have 2 in 112 years, 1 over 56. And that's why it sits halfway between the 1 over 30 and the 1 over 100 lines. And this is plotted in log space in the y-axis. And the idea is that these earthquake models that we generate are going to, we're going to assume that earthquakes in them obey a power law magnitude frequency distribution, cumulative distribution. This is called the Gutenberg Richter Law for short. It's empirically based, based on a lot of observations of data sets around the world throughout the last century. And it states that for every earthquake you get that's, for example, about an 8.0 or greater, you should get about 10 7.0s or greater and about 100 6.0s or greater if you're looking at a big enough region. And it might not be exactly 10 to 1 to 100, but it's usually some kind of power law relationship, a power of 10 or something like that. And the relative frequencies of small and large earthquakes in such a scaling are expressed by this factor B, which is called the B value. Here it's 1.0, which is exactly 10 to 1 to 100. That's actually a pretty good global value if you look at the whole globe, but we're going to explore a number of different values. So we're going to further assume that in our long-term earthquake models, the earthquakes will obey Gutenberg Richter scaling up to a maximum earthquake magnitude that they do not tend to exceed on the long-term average. Here it would be 8.0. So we say that on the long-term average, there aren't very many earthquakes above 8.0. There are so few of them that we don't need to factor them into moment balance or seismic hazard. Now, what Molnar 1979 showed is that given a maximum magnitude and a B value and knowing the geodetic rate at which moment is accumulating, you can actually constrain in closed form the rates of all earthquakes of any given magnitude. So this is what this line does here. We would have one 5.7 or greater somewhere in Anatolia about every year. We would have one 6.7 earthquake or greater somewhere in Anatolia once every 10 years, one 7.7 or greater earthquake in Anatolia once every 100 years, and so on up to 8.0, which would have a recurrence interval of 190 years. So this is a long-term earthquake model. Cool, we're done, right? Well, the problem is that this completely depends on what you assume for being Mmax and as well as the B value, as we'll see. So if I assume 8.5 instead of 8.0 for Mmax, you don't need as much of every kind of earthquake within the system because you have these big monsters that are coming along every so often and releasing a lot of slack. Likewise, if you cap Mmax at being 7.5, you need more of every kind of earthquake because you don't have anything at the top end that helps out. So that'll completely depend on what you assume for the maximum magnitude. It also will depend on what you use for the b-value. This is a little bit easier to constrain from the seismic catalog. There are good methods for doing this, but it will co-vary with what you estimate for being the maximum magnitude will co-vary with this. And so what we want to do is we want to iterate over a large suite of models with a range of M max, B, and other parameters. And for each model, we're going to compute the probability that that model would happen to produce this exact distribution of earthquake sizes that we've seen in the instrumental catalog if you were to let it go for 112 years. For example, that it would produce exactly one 7.8 earthquake, one 7.6 earthquake, 9 6.3s, and however many of other magnitudes are in the instrumental catalog, and so forth and so forth down to the cutoff magnitude. Now, what you can probably recognize is that that's going to be an extremely small probability, because what is the likelihood that your model would happen to generate exactly 31 5.6s instead of 32 at the same time as generating exactly 24 6.1s instead of 23? Well, the idea is that it's slightly less unlikely that the best long-term models would be able to do exactly that. And that's how we would be able to tell that they are better long-term models. It would be slightly less astronomically unlikely that they would happen to have produced the exact seismic distribution of earthquake sizes that we've seen. So it's a direct calculation of probability. Practically speaking, this also gets, the numbers get less wacky when you incorporate magnitude uncertainties, which we do. So we're not requiring exactly 31 4.6s and no more, no less, because there might be 27 or 35 of them, as some of the 4.6s in the catalog might actually be 4.7s or 4.5s and so on and so forth. And we account for that. And by the way, we do this down to a magnitude of completeness of 5.2, which we estimate from ZMAP looking at the catalog post 1964 when the network was upgraded. So what you can do with this is you can build up a space of a surface of maximum magnitude that you assume, b-value that you assume, and the total misfit of each of these gray models that you're iterating based on that probability, unlikely as it, low as it may be. And you can just build up a misfit surface, and then you can use that to constrain the two-dimensional PDF, among other things, of the maximum earthquake magnitude, likely in Anatolia on the long-term average, and the recurrence interval of earthquakes of that magnitude. This is an example actually from Los Angeles from earlier work, but the idea is the same, although this calculated probability is differently. So the probability of each model that we evaluate is this probability of it having reproduced the exact seismic distribution of earthquake sizes, times the probability that it achieves moment balance, times the probability of the moment balance, right? So to clarify, this probability is what we just looked at. It's this part down here. This is one by definition, because all of these models by definition balance the moment budget. And then this is the likelihood of that moment buildup rate being the actual moment buildup rate. And we can estimate a PDF on the moment buildup rate from the geodesy to get some uncertainties on how fast moment is accruing. So we multiply everything by that sort of prior. And so we work completely in probability space, and I'll just go right to the first part of the result. So this is the two-dimensional PDF of the maximum earthquakes magnitude and recurrence interval in Anatolia over the long-term average as estimated with this method. So the color of the PDF, the darkness, gives the probability as shown by this color scale here. And you can see that it peaks in the high 7s to low 8s range with a mode at about 7.7 once every century or so. And that's consistent with the Erzincan earthquake, which was about a 7.8. Again, the reason Mmax can actually be lower than the 7.8 is because we allow for those magnitude uncertainties in this calculation. So it just happens that 7.7 is the most likely to do the whole job of the whole catalog. And this is the long-term average weighted mean magnitude frequency distribution. Going down the middle here, this gray dashed line, and the 16th and 84th percentile weighted magnitude frequency distributions for the long term. So this is what you could use, for example, in a seismic hazard model for this region. And you can see that the rates of earthquakes would in the 5 to 6 range would be a little bit higher than what we observed, and then a little bit lower than what we observed in the 7 range, and similar in the higher range. This is the one-dimensional PDF of the maximum magnitude, which again peaks at a 7.7, although it's marginalized. But that does agree with the 2-dimensional PDF, and it has a weighted mean of 8.2 because it is this long tail, so you can sort of go with your favorite statistic of expressing where the real probability lies. And then this is the one-dimensional PDF of the recurrence interval of Mmax. And this is all possible Mmax magnitudes, not just 7.7. So again, it has this huge long tail at the top end, but it peaks at a century and change, which is consistent with the 2-dimensional PDF. And you can also estimate the b-value using this method, which peaks just north of 1.1. Now, there's been some discussion going around in the community about what the most appropriate form of the long-term magnitude frequency distribution is mathematically. This is a form that truncates to right at 8.0 in terms of the rates of earthquakes greater than or equal to each magnitude. We've been exploring this alternate model in which it's the rates of earthquakes of each magnitude that gets truncated at the maximum magnitude, which may be more or less plausible considering various things. This has its original inspiration in the work of England and Billum 2015, and it was probably almost correctly derived in a GRL paper that I worked on last year, but this equation needed to be greater than, not greater than or equal to, but that I'm still confirming. So, but this model has this taper at the top end near Mmax. And for that reason, we can't very well estimate the 2-dimensional PDF of Mmax and its recurrence interval here, but we can still estimate the 1-dimensional PDF of Mmax, which gives us about an 8.1 to 8.3. Again, those would be rarer in this formulation of things, so you would not need to worry about them as much, but they would still be there. It's more useful, however, to look at the recurrence interval of earthquakes exceeding magnitude 7 3/4, which would be about the magnitude of the Erzincan earthquake. Those would tend to come around every century, or it's every 2 to 3 centuries. And again, you can estimate the b-value just like the previous formulation. So as far as what we want to do in the future, one thing these models assume, which is important, is that all earthquakes occur independently of one another, because these are all calculated with Poisson probabilities. Now that belies the fact that earthquakes on the North Anatolian fault, as well as elsewhere in Turkey, have defined this westward propagating sequence in the 20th century that is well known and well studied. And it has most recently, with the Izmit earthquake of 1999 here, which would sort of fill in this gap, as well as the Düzce earthquake. We don't currently incorporate earthquake sequences and their influences on one another into this, so that's something we want to work into the probabilities going forward. Another thing we want to do is think outside the box, literally. We want to move away from drawing a giant box and saying the moment is balanced inside that, because where do you draw the box? Where do you draw the boundaries? It's pretty arbitrary. And do you draw them along tectonic boundaries? Well, how can you be sure? There might be a distance over which you can draw boundaries for a given magnitude or a given size fault, and that's something we're going to be looking at. It also still matters when your catalog starts. For example, if our catalog started in 1940 and we missed the Erzincan earthquake, our probabilities would still be different and would still be thrown off by that. Same problem if your California earthquake test starts in 1905 or in 1907, as you can probably imagine. So the solution will probably be to take a bunch of pieces of the seismic catalog and play this game with those. And then eventually we want to bring this to the rest of the Alpine Himalaya belt and map strain rate to seismic hazard there. And I'd like to thank all of you for your time and attention. I'm going to stop there and we'll take questions. And I'd like to especially thank Jonathan for all the work he's done making this possible and for being an awesome mentor in this process. So thanks, man, and thank you, everybody, and thank you, everybody online.
Thanks, Chris. That was fascinating. So again, there's about 10 people. Shouldn't have said that. Okay, there's tens of people here in the room, yeah. And also I think we can bring up a chat window, and It's been an hour, so let's try to not spend too much time, but if there are questions from the audience or from either audience, the World Wide Web or the...
Yeah, you guys can start typing questions as you like.
Just for the catalog you're using for the common estimations, was it only for the normal Anatolia topic?
Oh, sorry. Yeah. It is for all of Anatolia, so it covers it actually covers a wider region than this Anatolia box, but we clipped it at the edges of this box. But it extends also into part of the Aegean and I think somewhat south. They wanted to get everything anywhere close to Turkey for the Turkey National Seismic Hazard Maps.
So that was someone in Martin in Potsdam asking about the geographic extent of the catalog that he was using and how large that is. So there's been a question from Nick D'Agostino. Hello. Can we account for the aseismic component of deformation?
Yes, I forgot to mention that. Thank you. We also iterate over how much work aseismic deformation does within the moment balance. We have a PDF of that. And we iterate over different values in that PDF. We peak it at 80% seismic deformation, 20% aseismic. That's based on evidence that the ISMIT post-seismic deformation released perhaps maybe 25% of the moment release of the main shock itself. And I think estimates vary for the Van earthquake, but I think one of them is around 27%. Depends on how long you look. That is another thing that we're going to be exploring more in depth as far as how uncertain is that, and does that vary from earthquake to earthquake and place to place? Like, do small earthquakes have post-seismic deformation? I'm not sure. Yes.
So another question is, how would the 1939 earthquake affect your estimation with or without this event?
That's worth running for sure.
Is it not included?
No, it's included, and it's always included. So, for example, if the catalog were to start in 1940, it would the probabilities would be different. Now, if the 1939 earthquake is right on the line defined by the other earthquakes, the probabilities are, in terms of being on the Gutenberg Richter relation, the probabilities are probably not going to be that different. Like it's not going to, it doesn't look that weird. If it doesn't look that weird in magnitude frequency space, it's not going to throw things off too much. But it is still quite important for this analysis. And so that's something that we want to iterate over. We do assign some magnitude uncertainty to 1939 because some estimates say magnitude 8, some say, I think, magnitude 7.6. So we give pretty generous magnitude uncertainties, which will somewhat counteract its effect.
I see two more questions. So I'll ask Jonathan Bedford from GAPZ asks, in terms of estimating hazard, why don't you assume asperity sizes along the fault based on historical seismicity and then back extrapolate current strain rates to estimate which asperities are mature?
I think that's a great idea. I'm not sure why we don't do that. That's a great suggestion. That might also help deal with, or not deal with, but at least place some, give us some guidance on whether the assumption, which I also should have mentioned, we assume that strain rates are constant in time in this analysis. We assume that what we see in the geodesy right now is characteristic of the long term. Now, Ekbal Hussein's work has shown that actually may be a good assumption, at least along the North Anatolian fault, that post-seismic might throw things off for 8-10 years, but then it goes back to interseismic rates, and most of the interseismic anytime might resemble what we see now. But it might not perfectly do so, and if, depending on stress transfer and other factors, the strain rate, strain accumulation rate, not only at the surface, but also with depth may also change with time. And I think that's a great idea. Thank you.
I can put you guys in contact.
Okay.
So there's another question. I think this is the last one. Is there any other questions from the audience here? So someone's asking, how do you deal with the step term in GNSS displacement time series data? So can I answer this?
Yes.
This is a good question. It also applies actually to the InSAR data. So, we're looking at 5 years of line of sight velocities. To my knowledge, there's been no very large earthquake. So it's also, our time series estimation stopped prior to this most recent one. So these data sets end in about October 2019. There could be earthquakes within those data. We do when we look through the interferograms, we tend to look for things like this. Perhaps these would result in unwrapping errors that would get discarded during the Lickspass culling criteria. Also, in terms of the GNSS, this is one of the reasons why we're using the NOK plus England compilation as opposed to the GSRM compilation. So it's far fewer sites. There's been a very careful culling criteria invoked that's discarded many sites. And we've also seen discrepancies in the GSRM data where you have two co-located vectors pointing in slightly different directions that perhaps could result in a high strain rate localization. We're also fearful that it's contaminated by some of the vertical measurements that we've seen from the up velocities. But this is a problem that we need to deal with. A lot of these published GNSS data sets that are used to do things like strain rate estimation aren't necessarily culled, or meaning that careful attention hasn't been paid to try to eliminate co-seismic, post-seismic deformation. This is a whole nother can of worms. What is interseismic deformation, and can you be confident that a velocity field is actually, a GNSS-derived velocity field is actually representative of a interseismic velocity field? So it's something that we've thought about with the Turkey data, Anatolia data, and it's something that we'll continue to think about as we look to expand sort of to other parts of the Alpine Himalayan belt and elsewhere in the active tectonic regions. So someone's asking, this will be the last question, I think, is that using only InSAR, will it be possible to map deformation on a north-south oriented fault plane? Well,
That gets tricky.
if it's dip-slip deformation, so if it's thrusting or extension, normal faulting or thrust faulting, for sure, because the motion is in the east-west direction. I assume that you're talking about north-south. So there are techniques, for example, so the more look angles you have, the more constraints you can place on deriving 3D velocities. So some people are perhaps looking Sentinel I data in both directions. They're maybe incorporating TerraSAR, ALOS data, slightly different look angles, and you can start to decompose with confidence to get north-south. There's also a long track pixel tracking to get north-south displacements using a slightly different technique. So it's not interferometry per se, but you can do north-south deformation. And actually what we're starting to see, perhaps some of these other components of the strain rate tensor can help point towards deformation that might be in sort of non-optimal InSAR orientations. So Tim Wright is saying there is some sensitivity to north-south, but it trades off with vertical without doing the along track methods that I was sort of alluding to. Did you ever?
Yeah, another thing you can do, if you have an earthquake or something like that in an arid region, if you have sort of an ideal case, you'll have quadrants where the deformation goes out to 45 from the fault plane. And if you have a good signal where it's clearly going this way and coming in this way out here, and then going this way and coming in this way out here, you might be able to use those quadrants to at least do something like that for an earthquake, assuming you have no other data, and figure out the approximate dimensions of the fault plane and perhaps even how deep it's propagated.
Okay, so it's been about an hour and 5 to 10 minutes. Thank you everyone, both here in the audience and at home or in the office. This webinar will be posted on the COMET YouTube channel probably by the end of the week or early next week. So stay tuned, and also stay tuned for future upcoming webinars from COMET. Thank you guys.
Yeah, thank you so much.